All right, continuing further, now let's look at direction numbers, and this involves a note on these examples that we just covered. So the vector equation and parametric equations of a line are not unique. If we change a point or the parameter, the parameter t, or choose a different parallel vector, then the equations change. For instance, if instead of 5, 1, 3 in this example there, we choose the point 6, 5, 1. In other words, choose this point here. This is also on the curve. In example 1, then the parametric equations of the line become, instead of this 5, 1, 3, it becomes this x equals to 6 plus t. Remember that other one's going to be the 5. Not the 5. It's going to be, this was y is equal to 1. Let's go back here. So 1, 1 plus 4t, and this one's 3 minus 2t, but then this is not going to be 1 anymore. It's going to be 5. It's going to be 5 now, because we're switching up this 1 with this 5. So it's going to be 5. Y equals 5, and this was going to be minus, not the minus, this is plus 4t. 4t, like, and then z is equal to, this is going to be now 1 instead of 3. 1 minus 2t. So, or instead of switching up the starting position, or if we stay with the point 5, 1, 3, so we stay with this one, but choose the parallel vector 2i plus 8j minus 4k. And again, this is just a scalar multiple of this. We just multiply everything by 2 here. By 2, 2 times 2 is 4, 2 times 4 is 8, and then right here, negative 2 times 2 is negative 4. If we do all of that, we arrive at the equation. So x equals to, starting point is 5, plus, and instead of t, we're going to multiply by 2, it's going to be 2t. The next one's be y, is going to be 5, 1. And this is going to be plus 4, instead of 4, it's going to be 8j. 8t. We just switch up the parameters, the parametric equations. And lastly, z is going to be 1 minus 4t, like that. Actually, whoops, that's the one over there. That's this one. This is 3. So 3 minus 4t. So in other words, these all represent the exact same line, because this is another parallel vector, and there's another point on that line already. So we get the same line, just different equations for it, but same thing. Alright, so in general, if a vector v equals to components a, b, c is used to describe the direction of a line L, then the numbers a, b, and c are called direction numbers of L. Since any vector parallel to v could also be used, we see that any 3 numbers proportional to a, b, c could also be used as a set of direction numbers for L. So you could switch them up to whatever they are, as long as they're proportional, or in other words, scalar multiples of each other. And you can use this as the direction numbers, and then with any point, any starting point in this equation that's on the line. All right, now let's continue further. So symmetric equations of a line. So another way of describing a line is to eliminate the parameter t from the parametric equations. So if none of a, b, or c is 0, we can solve each of these equations for t and equate the results and obtain. So what I mean by this is we can get rid of these parameters t like that. So if we go back to our vector equation, or just our parametric equations, we had, before the example, we have x equals x naught plus at, and then y equals y naught plus ab, and this is actually at, and bt, get that mixed up. So anyways, if we have this, let's go back here, and so if none of them are that, we could rearrange it. So if we have x is equal to x naught plus at, now we could solve this for t. So move this over to this side and then divide it out. And then divide this out like that. I'll just put a division sign. So this one we subtract, this one we divide, so we get a t is equal to x minus x naught over a, like that. And then the next one is y is equal to y naught plus bt. And then likewise, we do the exact same thing, move this over, and then divide this out. We get t equals to y minus y naught over b. And then last one, z is equal to z naught plus ct. And then rearrange this, move this over, just for completeness, put the arrows in. T is equal to z minus z naught over c. All right, and then thus put these all together. We get t is equal to, and then equate all of these together. And they're symmetric because they're all the same. They're all equal to t. X minus x naught divided by a is equal to t. Well, these are all t. If y minus y naught over b equals to z minus z naught over c. And then we can box these in like that. Yeah, so these equations are called symmetric equations of the line L. So notice that the numbers a, b, and c that appear in the denominators of equation 3, or I'll just call it the equation above. Equation 3 that was labeled by the calculus book, but I just like writing this, the equation above here, are direction numbers of L. Yeah, so note that these are the direction numbers. Remember the vector v, a, b, c. Those are direction numbers of L. That is components of a vector parallel to L. So if one of a, b, or c is 0, because then you can divide by 0, we can still eliminate t. For instance, if a equals to 0, we could write the equation as follows. So instead of this, we can't do this. But if a equals to 0, we could just start off with x equals x naught, and then the other ones leave that in. So we could write. So if we have, for example, if a equals 0, we have x equals x naught plus a t. So this goes to 0 because a is 0. I'll just leave it like that. So then this equals to this will just be x naught plus 0 like that. So in other words, we get x equals to x naught. Or else I'll do that after. Just make it for completeness. This equals to x naught. So what we get is the equations x equals to x naught, and then we have the symmetric equations y minus y naught over b, because these ones are non-zero, and then z minus z naught over c. And there's our new symmetric equations. And now this means that L lies in the vertical plane x equals x naught. And here I'm actually going to draw this out just to illustrate this. So it lies on the x equals x naught vertical plane. So for example, if you had a just xy graph like this is the y, this is the z, and I'm just going to draw a plane like this. And then this is going to go through it. This is the x naught, this is x. And then this plane right here goes across like that. And let's say at this point right here, let's say this point crosses through it. This is at x naught. So this means that the line's going to be on this plane, and it's going to be something like this. That's going to be our L. Like that, or it could be like this, etc. It doesn't matter, but it's going to be on this plane, like that. And that's how you write this, x equals x naught. Yeah, so it doesn't matter what z or y value there are, you're always going to be on this x naught vertical plane. Alright, so let's continue further and look at example 2. And this one states, find parametric equations and symmetric equations of the line that passes through the points A, which has coordinates 2, 4, negative 3, and the point B, which has coordinates 3, negative 1, and 1. And then part B states, at what points does this line intersect the xy plane? Alright, so let's go over number A first, or question A, so solution to 2A. Let's first graph out the lines to better visualize this. So it's going to look something like this, and this is our Z, And this is our y. It's going to look something like this. Our y is going to be like this. And actually extended it past on the negative side. And let's say we have our x is going to be like this. Like that. That's our x. And so now let's graph out the point A. Yeah, so the point A goes to 2, 4, negative 3. So it goes 1, 2, and then it goes to 4. 1, 2, 3, 4. And it's going to go on the negative side now. So I'll draw this like that. And it's going to go, 1, 2, 3. So it's going to look somewhere like this. If we draw it across there, it's going to be like this. This is going to be our point A. Like that. And then the point B is going to be 3, negative 1, and 1. So it's going to go to 3 here. And then it's going to go to negative 1. So it's going to go back 1. And it's going to go up 1. It's going to be up like that. So it's going to be somewhere around here. Let's see if we draw it in 3D. It's going to be, this is our point B, like this. And then the line is going to be across like that. All right, and this is going to be our line L. So just fix it up, write A right here. And A is, again, it's going to be at 2, 4, negative 3. Like that. And then the B is going to be, the coordinates are 3, negative 1. And 1, like that. That's B. And then, and also in part A, it says at what points does this line intersect the XY plane? So it's going to be somewhere, it looks like somewhere around here-ish. Like that. That's, I believe, something like that. But anyways, I'll erase this, and then until we get it exact. So now let's go further. Alright, so going further, so we're asked to find parametric equations and symmetric equations of this line passed through these 2 points. So we're not explicitly given a vector parallel to the line, but observe that the vector v with the representation AB, so from here to B, is parallel to this line v, to this vector, or the direction vector. Actually, no, I mean parallel to the line, yeah. This is the vector, yeah. So it's parallel to this line right here. And we can write that out. That's just going to be v. It's going to equal to, well, the difference. It's going to be our position vector. V is just equal to, so it's going to be from, A to B. So we're going to go 3 minus 2. Like that. And then negative 1 minus 4. And then 1 minus 3. 1 minus negative 3. Like this. This is going to be 1 minus negative 3. Yeah, so this one minus this last one. And then just solving this is going to be 3 minus 2 is 1. Negative 1 minus 4 is negative 5. And then 1 minus negative 3 is going to be 1 plus 3. That's going to be 4. Like that. Alright, so thus the direction numbers are just the components of this parallel vector. So B, A is equal to 1, B is equal to negative 5, and C is equal to 4. And then taking the point A as a starting point right here, A is 2, 4, negative 3. As P naught, we see that the parametric equations are, and remember this one, the parametric equations are just going to be x equals to x naught plus AT, then y equals to y naught plus BT, and then we have Z is equal to Z naught plus, this is going to be CT. And then where these Z naughts, etc., it's going to be this PO, and that's going to be choosing our point A. So this means that x is going to equal 2. It's going to be 2 is x naught, it's right here. Then plus A is 1t. So this is going to be plus t. Yeah, 1t, like that. And then y is going to be, this is y up. Yeah, so y is equal to y naught is going to be 4 plus, it's going to be negative 5 right here. So negative 5t. And then lastly, z is equal to, z naught is going to be negative 3. And then it's going to be plus c, which is 4t. Oh yeah, this is a 4 right there. And yeah, this is the negative 3 right here. Alright, and box this in. These are parametric equations of that line. Alright, so that's a parametric equation. Now the symmetric equations is just when we make t equals to each other. So we'll just make this, move this over, x minus x naught over a, then divide this out, etc. Do that for all of them. And essentially we just get that same setup here. So we get t is equal to, again, x minus x naught over a. And this equals to the same thing for the y. Do the same thing here. Y minus y naught over b. This equals to z minus z naught over c. And this will equal 2. Well, we know x, yeah, x is just general. X naught is just 2. So there's 2, then 4, then negative 3. And then this is divided by a, which is 1 here. Like that. This equals to y minus 4 over negative 5. This equals to z minus negative 3. That's going to be plus 3. Negatives become positive, yeah, with 2 negatives. And then divide this by, this is c, 4. Like that. So there it is, our symmetric equations. Alright, so now let's take a look at the solution to B, and yeah, let's go over here. So again, yeah, we solved the parametric equations, symmetric equations, solution part A. Now part B says, at what points does this line intersect the xy plane? Alright, so that's a key factor. So the xy plane, like this means it's going to be this whole flat section actually. So that means to pass it is when z is equal to 0. Yeah, so it's going to be actually somewhere here. Yeah, so that's actually the point. It goes through the z equals to 0 setup across it. So what we could do is solve that. So the line intersects the xy plane when z is equal to 0. So we put z equals 0 in the symmetric equations and obtain. So we have these symmetric equations, put z equals 0 there. So we get x minus 2, yeah, divided by 1 and just ignores it. Divided by, equals to y minus 4, divided by 5 is equal to, well, z is 0. 0 plus 3 over 4. Well, again, this just equals to 3 over 4. Like that. Yeah, so then we solve it for each one. So we'll have x minus 2 is equal to 3 over 4. And then move this 2 over to this side. We'll get, well, plus 2. And multiply top and bottom by 4. So we have the same common denominator. This equals 2. Actually, we'll do that after. So we move it over. And then we're going to have x equals 2. 3 over 4 plus 2. Again, times by 4 over 4. Like this. Right, it's a bit neater. The 2 here times by 4 over 4. Like that. I'll just move that up. So then 2 times 4 is 8. Plus 3 is 11. So 11 over 4. So I have the same common denominator like that. And box this in. So that's our x value. And then the y value is, well, we equate the other side. Y minus 4 over negative 5 is equal to 3 over 4. It's equal to 3 over 4. Yeah, 3 over 4. Let's fix that up. And yes, move this around. So then multiply this by negative 5. Yeah, we move over this negative 5, multiply it out, and then move the 4 in. We'll get an equation for y. So in other words, we'll get y is equal to, we'll put the negative there, so negative 3 over 4 times by 5, and then minus, well, the minus becomes plus 4, like that. And then again, same common denominator, so times by 4 over 4, and 3 times 5 is 15, so we're going to get a negative 15 plus 16 over 4, that just becomes, this is negative 15, like that just becomes positive 1. 16 minus 15 is 1. So 1 over 4, like that. Alright. Yeah, so thus this means that, well, we have the equations, x is going to be equal to 11 over 4. That's just right here. And then we have y is equal to 1 over 4, where again z is 0, because it's crossing the xy plane. So then the point, we'll call this P, has coordinates, and this is going to be 11 over 4, 1 over 4, and 0, like that. Yeah, so thus the line intersects the xy plane at the point P, and then it has coordinates 11 over 4, 1 over 4, and 0. And we could draw that here. So then this is our point P. This is 11 over 4, 1 over 4, and 0, like that. Yeah, so 11 over 4 is going to be, well, 12 over 4 is 3, so it's going to be between 3 and 2. And then there's this 1 over 4, it goes pretty much like this, around there. It's going to be somewhere around here, actually. Let's just erase that. It's going to be somewhere around here. And move this over. And yeah. Alright, so that's the point. And let's continue further, and we can graph this out. So let's double check the graph using the GeoGebra 3D graphing calculator. So here you can make a line just from 2 points, 2, 4, -3, to 3, -1, 1. And it gives you the actual equation of the vector equation as well. And then I put the points on it, and it shows the, and then I graph the point as well, 11/4, 1/4, and 0, and see where it lands. So there's the line. Yeah, it looks exactly like what we had. There's our A, there's our B, and then there is the p-value right there on it. That's how the line looks like. Again, you can click the line, play around with it. So let's continue further and look at a note on example 2. So in general, the procedure of example 2 shows that that direction numbers of the line L, through the points P0, which has coordinates x0, y0, z0, and P1, x1, y1, z1, are, so direction numbers are x minus x0, y minus y0, and z minus z0. And so the symmetric equations of L are. And again, you can see that here because we were looking at the direction numbers, the A, B, and C. So this right here, A, B, and C. And we solve them by the difference of these 2 points. So this 3 minus 2, that's going to be, well, we can consider this as this is going to be, as x1 minus x0, and then x2 minus, and then y2 y1 minus y0, and then z1 minus z0. And those are the direction numbers there. So in other words, we could write this equation as, instead of A, we could write x1 minus x0, etc. So we could write it like that, because that is what it was. So 3 minus 2, that's just x1 minus x0. Alright? So let's write these out. So we could write this all out. So we're going to have x minus x0 over, now the direction numbers are x1 minus x0. Then likewise, it's going to be y minus y0 over y1 minus y0. This equals to z minus z0. Then z1 minus z0. Like that. So epic stuff.